looked like it was the
So this morning we're going to talk about, in lesson number 4, describing the extensible authentication protocol. As I mentioned previously, there are actually many different variants or versions of this particular protocol and many different ways to actually implement 802.1x in your wireless network. So if you want to be able to identify which version you want to use, you have to have a good understanding of the differences between those different protocols. It's a very important concept. So in this lesson, what we're going to talk about then is how we compare some of the common EAP types that you're going to see. We'll take a look at the main 802.1x and EAP families. I mean, there are many different flavors of the extensible authentication protocol, more than we would need to discuss in this particular class, but we'll certainly take a look at some of the common ones. We're going to explain the purpose of certificates in this process, right? Certificates play a role as well. So we'll take a look at the certificates and what kind of role they play in this process. We'll talk about the public key infrastructure, the terminology that you're going to see with PKI, the different components in wireless networks for PKI. And we'll talk about how PKI actually works with the extensible authentication protocol specific to what we're doing with wireless networks. We'll take a look at EAP-TLS. That's the extensible authentication protocol with transport layer security. And obviously, if you're familiar with SSL, TLS is a very similar process. I mean, it's a little bit more advanced. Obviously, it's the newer version of the secure socket layer. We'll talk about the protected extensible authentication protocol and how that works with wireless networks. And then we'll also talk about EAP-FAST. And EAP-FAST is just another variant, of course. That's the extensible authentication protocol that we typically see with this process. But there's lightweight extensible authentication protocol, there's EAP-MD5, there's EAP-OTP, there's EAP-PSK. There are just many different versions. EAP-FAST is the flexible authentication secure tunneling protocol, and so on. So we're going to take a look at a lot of different versions here and really identify which one it is that you would actually want to use in your environment. All right, a key element of any kind of authentication, as I mentioned yesterday, is making sure that the credentials that the client sends can be read by the authentication server and are sent to the right authentication server, right? Those credentials can be encrypted before being sent so that we can make sure that they're not compromised. And there are really two types of encryptions that exist. We talked about this yesterday as well. Symmetric encryption, where you're using the same key to encrypt and decrypt, and asymmetric encryption, where you're using a key pair. The keys are related to each other, but one key is used to encrypt and the other key is used to decrypt. And the nature of that relationship depends on what it is that you're trying to accomplish with that particular process. So we will talk about many different aspects of that today, all right, and get into some details. And then we're actually going to do some implementations a little bit later on. We'll finally get into our lab exercises today where we start to implement some of these concepts. It means essentially that the same algorithm and the key that are used to encrypt and decrypt, that is the symmetric process, right? When we talked about the symmetric keys, that's what we see on the slide here. We've got a plain text message. Both Pat and Bob share a common key. The clear text message gets encrypted with the key, which is called the crypto variable. The ciphertext is the end result of that. That ciphertext gets transported, and then on the other side, we decrypt with the same key. There are many, many different types of encryption, but in many ways that we can do this symmetric process. AES, for example, is a symmetric encryption algorithm, DES, triple DES, and so on. It is a simple method of encryption and decryption, which means it's fast. We talked about this yesterday as well. Fast encryption algorithms are generally better suited for data transport, whereas asymmetric processes are better suited towards key exchange and digital signing and whatever else asymmetric processes are applicable to, right? We talked about asymmetric, the asymmetric key process. It's a lot more robust. The mathematical concepts are a lot more complex. With asymmetric keys, we always have a pair of keys, a public key and a private key. And that's what we see in this particular example. The public key in this case is key 1, and the private key in this case is key number 2. These keys are actually built on a mathematical algorithm. One key is derived from the other key. As an example, you guys are probably familiar with this when you deal with things like certificates for a website, and you use the public key infrastructure to establish those certificates. That means you're sending something called the CSR, a certificate signing request. So what happens is you generate a public certificate, and then you send that public certificate to your certificate authority or registration authority. A registration authority is a subordinate to a certificate authority, and they go through a verification process and they digitally sign that certificate. What's never shared with anybody is the corresponding private key that was generated as part of that key pair. So what is encrypted by key 1, and if you recall, key 1 in this case is the public key, can only be decrypted by key 2 and vice versa. So having only one key allows encryption but not decryption. So you think about the process, you say, okay, well, if key 1 is the public key and I'm encrypting with the public key, doesn't everybody know the public key? And that's very true. In its nature, public keys are public. That doesn't mean they're widely published, but they're not necessarily hidden. So they can be discovered and they can be captured. But the only way to decrypt information is by using the corresponding private key, which is never shared. So if Pat, for example, wanted to send data to Bob, and Pat wanted to hide that data so that nobody else could read that data, the first thing Pat would have to do is he would have to get Bob's public key and use that public key to encrypt the data. In addition, then Bob, once Bob receives the information, would then decrypt that data with his private key. Now you see here there's 4 keys in this process, and that's because both Pat and Bob have their own key pairs, right? So Bob's going to have a private and public key, and Pat is going to have a private and public key as well. So that's what we're describing in this process. Having only one key doesn't, release or make the data available to read. So to understand how asymmetric keys relate to certificates, particularly in a wireless network, let's suppose that users, Pat and Bob, we'll just call A and B, want to exchange a secret message. Pat wants to make sure that Bob will be the only person that can read what he sends. And this is very common in a wireless network, right? We're sending our data over clear channels, unlike a wired network where we have some kind of assumed privacy because somebody's not sniffing the bits on the wire, but we're sending everything in open space, so we do need to encrypt that data. Pat generates a pair of keys, and we'll call that key 1 and key 2. which, by the way, doesn't necessarily have to be signed, right? We talked about going through the signing process. You only need to sign keys or get keys signed if you're concerned about authentication. You don't need to have a set of signed keys or a signed public key if you're concerned only about confidentiality and message integrity. Authentication is really the only reason a certificate or a key would be signed. So Bob's going to generate another pair of keys for himself, 3 and 4. So data that's encrypted by using key 1 can be decrypted only by using key 2. That means that key 2 is going to have to be, or key 1, excuse me, is going to have to be shared. Data that's encrypted by using key 3, in this case, can only be decrypted using key 4 and so on. The thing that's lacking on this particular slide is that they didn't really, I mean, they kind of allude to it here, but they didn't really give you a clear distinction of what is a private and what is a public key, right? But again, if I want to send stuff to Mike, and I want only Mike to be able to read that information, Mike is going to have to share his public key with me so that I can encrypt that data with his public key. And then he'll be able to decrypt that data with his private key and so on. So to exchange this secret message, Bob sends one of his keys to Pat, key 3 in this case, so we'll call that the public key from Bob's perspective. That's given over to Pat. Pat uses key 3 to encrypt the message because he knows that Bob, who's the only one that has key 4, is going to be the only person that can actually decrypt what he encrypts with key 3. Bob doesn't give away key 4, which is his private key. In fact, even in a signing request, even when something is being signed by a third party, we don't actually ever share the private key. All right? So when Bob wants to answer Pat, he asks Pat to send him his public key, in this case key 1, encrypts the message with that key, knowing that Pat can only decrypt it with his private key. So that is an example of using asymmetric cryptography for the purpose of confidentiality. But we can also use asymmetric cryptography if our goal is to digitally sign information. Now, digital signatures, not necessarily something that we see too often, but at least in a transmission of data, but a very similar process is to ensure that we have something called non-repudiation of origin, where we can guarantee that the data came from the right person, right? And in this case, that's what this process entails. If you consider the previous process, Pat sending data to Bob, Pat uses Bob's public key to do that, well, that doesn't guarantee that the data is coming from Pat, because anybody could have Bob's public key. So another concept is to utilize the keys in a different way. The public key, well, let's say, for example, that Bob wants to make sure that the information is coming from Pat, right? So what if Pat added a secondary process to this communication? Not only did Pat encrypt the data using Bob's public key, but Pat also hashed the data using his private key, his own private key, which Bob can then verify that hash with Pat's public key. By doing that, Bob can essentially be assured that the data came directly from Pat, because the only way that hash would have been generated is because of knowing that private key. And that's the only person that knows that private key is Pat. All right. You know, that level of security that we talked about on the previous slide is great for message exchange. We know we can give our public key to anyone who wants to send a message. We know that there will be the only one that he's going to be the only one, or I'm going to be the only one that's going to be able to read that message that's encrypted with my public key. I can even, feel comfortable that my public key is literally public and it can be viewed by anybody. The only thing that I have to protect is my private key. So public keys are generally made widely available, and the private keys are the ones that are kept secret and used for the secure exchange. A server, when you're connecting to a server, for example, on the internet, sends its public key to the client. And then we use that key to encrypt a password, knowing that only the server will be able to decrypt the password. That's kind of how SSL and TLS works. We need to be able to encrypt the channel, to encrypt the data. And we already talked about this. Asymmetric processes are not very good for establishing bulk encryption. They're slow, they're mathematically complex, so they're not really conducive to large amounts of data exchange. So rather than using this private and public key pair to encrypt our bulk data and send that data back and forth, we use the private and public key pairs to exchange a shared secret key. So what happens is Pat will, because remember we're going to be using AES. With WPA2 we're using AES as our bulk encryption standard. AES is a symmetric encryption algorithm, right? Which means we have to have a shared secret key. But how do we share that key without anybody else being able to see it? So Bob sends his public key. Pat generates a secret key, encrypts that secret key with the public key of Bob, sends it over, and Bob decrypts that secret key with his private key, and now we have a common shared secret that we can use for bulk encryption. It's a very, very simple process. It makes logically a lot of sense, but it's necessary in order for us to do this exchange. But like I said, in this particular system, the identity of the sender is definitely not protected. All right? If Pat wants to send a message to Bob, and if Bob receives that message, decrypts it, and reads Pat as the sender's name, he assumes that Pat wrote that message. But that really can't be guaranteed, because the public key that belongs to Bob could be used by anybody. So anybody can pretend to be the sender, in this case Pat, encrypt the data with the public key that belongs to Bob and post it, and Bob really has no way of knowing if Pat was truly the original sender. So the system has to become a little bit more complex, to ensure not only message integrity and message confidentiality, but also authentication, non-repudiation of origin. So Pat has two keys as well. What is encrypted with key 1, that would be his public key in this case, can be decrypted only with key 2, which is his private key. So the opposite would be true as well. What's encrypted with his private key can only be decrypted with the public key. So when Pat wants to send a message to Bob, he starts by encrypting it with key 2, which is his private key, and only key 1, which is the public key of Pat, can be used to decrypt that result. And in that sense, now we can be certain, Bob can be certain, that the message was actually sent by Pat. Does that make sense? I hope that makes sense. It's a lot of Bobs and Pats there, but the diagrams are not that great, but I think you guys understand the process. It's a kind of a twofold process. Completely different, but using the same architecture, right? This public and private key pair. So applying the public key that Bob allows Pat to encrypt the message with, what it ends up happening is that Bob can decrypt it, applying his private key as proof of identity. All right. What this is called is essentially signing the message with a digital signature or an electronic signature. All right. What do we do if we want to make sure that the keys are valid? In other words, we want somebody else to verify the authenticity of Bob or Pat. Well, that's where we come into the public key infrastructure and what we call a trusted third party. All right. Pat always applies his private key for encryption before encrypting the data a second time, right? We apply our private key for encryption so that we're digitally signing the data, and then we encrypt with the public key of Bob to hide the data, right? provides a much higher level of security, but but we still have to go one step further. All right, so there is one last step that's kind of applied to this process. What proves to Bob, for example, that the public key that he has for Pat is actually Pat's public key? It's kind of like you get pulled over by the cop and you have to present identification. Now you have a formal government ID called a driver's license that has various security standards built into it, holograms and all kinds of things that are applied to this driver's license that guarantees its authenticity from the state government, right? That's the state that's issuing that license. You wouldn't be able to take your college ID necessarily and present that as a form of identification and have that be trusted necessarily, because the third party that maybe created that ID is not necessarily a party that the police trust. Well, it's the same thing with certificates. I can generate my own public and private key pair and sign it myself. But that would be like me creating my own identification and laminating myself and giving it to the police officer. It's probably not going to pass muster, right? So what we have is we have to have a way that Bob can guarantee that the public key genuinely belongs to Pat. The best way to achieve this is to have some entity or some organization that both parties trust, or even more than that, that many parties trust, that verify or basically sign off on the identity of Pat. All right. Now, we can exchange those keys, and if Bob and Pat know each other, they live in the same neighborhood, that exchange is possible. But that's typically not the case, right? We're doing this exchange over public domain, which means keys can be intercepted and otherwise modified and so on. So what we do is we introduce this third person. Pat can give his public key to someone he trusts to bring it to Bob. But how can Bob be sure that that person he meets is the one that Pat sent? Bob is going to need another person to testify to the identity of that person. So let's simplify this a little bit. What has to happen is both Bob and Pat have to agree on a trusted third party. All right? In the case of public key infrastructure, that is something called a certificate authority. Or in some cases, a registration authority, which is just a subordinate to a certificate authority. All right? So the process, which I'm sure you guys are familiar with, if you guys are systems guys, you've probably had to deal with the certificate process in the past. But the logic applies. Because the authority is well known, the authority's public key is used to implement the signing process. That certificate authority is trusted. Now we have a way of verifying through a third party that Pat is who they say they are and Bob is who they say they are. Okay? And there are ways to also verify whether or not those certificates have been revoked. There's a couple of ways. A certificate revocation list, a CRL, which is more of a snapshot of revoked certificates, or we can use OCSP, the Online Certificate Status Protocol, which is a real-time verification process of the validity of a certificate. And I don't know, we need to get into the details of that. We may see that a little bit later on, but all right. So a certificate is a public key that a trusted third party has added a message to, like we talked about in the previous example. They basically signed that certificate. So each time the certificates are used on the computer or in a networking device, public keys get sent, the private key exists as well. And the certificates are used for, like I said, encryption, authentication, etc. So if PCA receives a certificate that PCB has issued itself, PCA can then use the certificate signature to verify that the certificate was issued by PCB via a third party. We see a picture of the certificate here. In this particular case, it says the CA root certificate is not trusted. All right. Now, that doesn't necessarily mean that it's signed by a party that we don't trust. It could be that we simply don't have the root certificate installed in our system. Most operating systems today, browsers and whatnot, that's why you tend to update them from time to time, have root certificates embedded in them, especially from most of the major trusted third parties. So you wouldn't have to run into the situation. But you may see this pop up in the case where third-party signatures are not necessary, right? So what we do is we self-sign our certificates. We see this a lot with routers and switches when we're doing SSH, where we're generating an RSA key pair, crypto key generate RSA, and then we specify the modulus and whatnot. In that case, we're actually generating a public and private key pair, but we're self-signing it. So we're not necessarily concerned about authentication in this point. We're more concerned about the process of exchanging a shared secret key for the purposes of AES and so on. When a wireless LAN controller reboots after its initial configuration, a certificate pair gets generated. That's a self-signed certificate because no external authority actually confirmed its validity. So when the administrator connects to the web interface of the controller for the first time, you guys will see this a little bit later on, a warning appears signaling that the CA for the certificate's not known because the administrator trusts the physical cable links to the controller that certificate can be accepted. It's more than that, right? We're also trusting that we know internally based on the IP address and based on the fact that we actually configured that controller is who they say they are, right? So we're not necessarily concerned about authentication. Same kind of concept that we see when we deal with, SSH connections to routers and switches. What provides this overall architecture is what we call the public key infrastructure, or PKI. That's our framework where we can base these security services, things like encryption, authentication, non-repudiation. But it's a scalable solution, and it's become really a critical component to any kind of security solution that we see today. So we'll go through a little bit of the terminology here. It's kind of easy to understand, but we need to make sure that you guys understand this because we're going to continue to build on this. And this is actually something that you may be incorporating in your environment as well, this public key infrastructure. So it's very important to understand that supporting framework and what that involves. It is a services framework. PKI is not a protocol. The whole purpose of this architecture or this framework is to support large-scale public key-based encryption. All right? It's a set of technical, organizational, legal components that are needed to establish this whole ecosystem of communication. The ability to scale public key cryptography, provide authenticity, confidentiality, integrity, non-repudiation, and so on. Two very important terms: the CA, which stands for Certificate Authority. That is the trusted third party that will digitally sign the public keys of the entities based on that certificate signing request. Now, you do have, like I said, subordinate RAs, registration authorities, but registration authorities generally don't sign certificates, but they will process data on behalf of the CA until it's kind of like the presidential secretary, right? I'll communicate with the constituents and I'll talk to the constituents, but when it comes to the final say, I have to go consult the big man in the chair, right? Certificate, that's essentially the document. That certificate is called an X.509 certificate. That's what it's referred to as today, okay? The CAs have certificates as well. that's called the CA certificate, and that's something that identifies their certificate authority. PKI is obviously more than just the CA and the people that use the certificate authority. The CA is there for key management. PKI users would be people, would be devices, servers, and so on. But we also have a lot of different protocols that are used to manage this process. We have storage of certificates. That's something that we have to be concerned about. We have a kind of a legal framework that defines how these certificates can be used. So let's talk about the certificate format first, and then we'll get into some of the other aspects. The X.509 specification is just basically a well-known standard which defines the basic public key infrastructure format. What does a certificate look like? What does a certificate revocation list look like? How is that formatted? And what is the interoperability that ensures that we have valid certificates? The standard has been used forever, right? It was applied to SSL originally when SSL version 1 was developed, IPsec functionality, so we can use this public key infrastructure for VPN technology, TLS, SSH, and so on. The X.509 v3 standards define the format of the actual digital certificate. And it's been used for many, many years, right? Web servers use X.509 v3 website authentication certificates using SSL and TLS. Web browsers use these certificates to implement client certificates in the SSL protocol. Mail agents are going to use this for things like SMIME and PGP. IPsec VPNs use this, and so on. So it's a widely adopted concept. In the CA authentication procedure, the first step of the user when we're contacting the PKI is to securely obtain a copy of the public key of the CA. I don't want to have my signature or my certificate signed by a CA if I can't also verify the identity of that CA, right? So the public key of the CA verifies that all the certificates that are issued by that CA are valid, all right? That's also distributed in the form of a certificate that's issued by the CA itself. This is called a self-signed certificate because the signer and the holder are the same entity in this case, and it's a root CA. But again, we trust that signature because there's an inherent trust in the CA, knowing that it's a published CA and they have a reputation for being a valid certificate authority. In this diagram here, Pat and Bob request the CA certificate that contains the CA public key. Like I said, typically that's going to be, if it's a browser scenario where you're just going to a website, that's going to be already embedded in the browser as part of the process of having that browser installed, right? But that may not be the case. We may actually have to go back and request that from the CA, okay? Once we receive the CA certificate, the system verifies the validity of that certificate using the PKI architecture. And then Pat and Bob follow up the technical verification that's done by their system by contacting the CA administrator, verifying the public key, the serial number, the lifetime, etc. of that certificate. So what happens if I need to get a certificate? How does Bob enroll and how does Pat enroll? Well, that's another step in the process. After I retrieve the CA certificate, both Bob and Pat go through 4 different steps to go through the enrollment process. Each of their systems actually generate a key pair, and they forward something called their certificate request, which includes the public key along with their identification information, right? All this information gets encrypted using the public key of the CA, which means that Bob and Pat's information is private because the only way that that information can be decrypted is with the private certificate of the CA itself. Once the CA receives the certificate request, CA administrators go through the process of contacting Bob and contacting Pat to confirm their identity, etc. The CA then digitally signs the certificate and issues the certificate with a lifetime back to Bob and Pat respectively. And then either the end user in this case manually retrieves the certificate, or we have an SCEP protocol that automatically retrieves the certificate. Then those certificates get installed on the systems. Bob's public certificate gets installed on Pat's system, and Pat's public certificate gets installed on Bob's system. Okay, so that is, you know, kind of a basic process, but that's how it works, right? And like I said, it's just part of any kind of public communication today, this public key infrastructure. The simple certificate enrollment protocol, the SCEP process is typically used. I mean, that's a protocol used for the enrollment and is a widely known and widely used protocol. But we don't have to get into the specifics of that protocol right now. Okay. So having installed the certificates, you know, having gone through the process, they're signed by the same CA. Doesn't necessarily have to be signed by the same CA, by the way, but does have to be signed by a trusted CA. They're now ready to authenticate each other. So Bob and Pat exchange the certificates. The CA is no longer involved in this process. We know that Bob sends his public certificate to Pat, and Pat sends his public certificate to Bob. Each party verifies the digital signature of that certificate by hashing the plaintext portion of the certificate, decrypting the digital signature using the CA's public key, and comparing the results. If the results match, then the certificate is verified as being signed by that trusted third party. So now both Bob and Pat kind of have an understanding of who's who. All right. So now that we've kind of gone through the whole process of talking about the general architecture, now let's see how this applies in our wireless network, because that's really what you guys are here for, right? Certificate authorities follow essentially the same model in this particular case. They're used to generate digital certificates for the clients, and if there are servers involved as well. The ICE server can actually be, or ICE can actually be its own certificate authority, or you can connect to an external CA. Certificate authorities have CA certificates that are used to validate that certificate authority. So ICE, for example, might be generating certificates for the communication process, but on ICE, we have a digital signature that's actually signed by a third party. So we can verify the identity of ICE, and as a trusted third party in this case, we can trust certificates that are generated by ICE as well. So ICE becomes essentially a subordinate certificate authority. All right. Clients request their certificate from the CA. They use that certificate to authenticate to the server using 802.1x. You know, extensible authentication, whether it's EAP-TLS or PEAP or EAP-FAST. The server requests, the servers themselves can request a server certificate from the CA, and that's used by the client to validate the authenticity of the server, and we can also use a self-signed certificate if we want to act as our own certificate authority. So what happens with a wireless LAN controller? As we said, once you go through the initial configuration process and setup process, the wireless LAN controller uses pre-installed server certificates, but you can set up the controller to request server certificates from a public CA as well. All right. Any questions so far? I think it makes sense, that that process. So let's wrap up this chapter or this lesson by talking about some of these extensible authentication protocol concepts. All right. And we're going to start with EAP-TLS in this case, and talk a little bit about EAP-TLS and what its function is. The EAP transport layer security was defined in RFC 5216. It's an IETF open standard. It obviously incorporates the use of transport layer security protocol. And it's very, very common in a lot of wireless networks today. It's actually the original standard wireless EAP authentication protocol. So it's widely adopted. It's still considered one of the most secure EAP standards that are available as well. TLS provides very strong security, but only as long as the user understands potential warnings about false credentials, and TLS is obviously going to be universally supported by a lot of different manufacturers of wireless LAN hardware and software. All right. In fact, up until 2005, EAP-TLS was really the only EAP type vendors needed to certify for both the WPA or the WPA2 standard. All right. There are client and server implementations of EAP-TLS in lots and lots of different vendors. Just about any vendor that you would use today would support it. And it's natively supported in Mac OS X 10 and above, Windows 2000, Windows XP, Windows Mobile, and so on. So you can get the idea that it's been around for some time, right? Apple iOS and so on. Unlike most TLS implementations that you would see, like, say, for example, over HTTPS, the majority of EAP-TLS requires a client-side X.509 certificate without giving the option to disable that requirement. You know, the standard itself does not mandate that use, but in the case of wireless communication, it's kind of incorporated. This places a little bit of a restriction on the overall functionality of EAP-TLS, but you know, it's still, you know, quite widely adopted as a standard. We know that certificates are used extensively in wireless authentication, especially if you're incorporating the use of 802.1x and EAP, because it gives us a way to authenticate and generate encryption material over this untrusted link. And like I said, EAP-TLS is definitely the most typical method of applying these certificates. You have to have a private and public key pair, and they have to be installed on both the authentication server and the client. Well, not the private keys, but so an authentication server pair of keys and a client pair of keys need to be generated and signed using this public key infrastructure. Then they get installed on the authentication server and the client respectively. Now, in the case of Cisco, this is important to understand, the authentication server has to be a Radius type server, but it can be ICE because ICE incorporates a Radius server, and that Radius server, by the way, then can be integrated with Microsoft Windows and Active Directory and so on. One of the technical difficulties that you're going to see with user certificates is that the key pair is stored on the client. Modern systems commonly use two levels of authentication. The client certificate is used first, allowing the client machine to be authenticated to receive encrypted data from the authentication server. The authentication server also sends a certificate. The user is then authenticated using a different method, whether it's a password, a token, or whatever it might be. The certificates that are previously exchanged between the machines are used to protect the user's credentials when they get transmitted back and forth. All right, so it is a complex process. I mean, it's no different than what we described over the last few slides. Is this something that you're going to have to understand as an implementer? Probably not. It's probably, you know, when you're establishing your security profile, it's nice to know what EAP-TLS does and why you would choose to use it, because you do have some other choices. All right. Now, TLS is no longer used in a lot of different environments. It was intended to be used as an alternative, standardized version of SSL. And of course, SSL has been long been used for a long time. If we use HTTPS, typically you're going to be using TLS version 1.2 today, and so on. So EAP-TLS uses a certificate to authenticate users, machines, etc. The certificates themselves are issued to the users and computers by the CA or a registration authority, like a local registration authority, like ICE, and are used to validate that particular identity. The maintenance of this is where it becomes critical, right? The maintenance of the CA, which is part of that public key infrastructure, could be a little bit overwhelming, kind of a barrier of getting into EAP-TLS, because maybe you don't have the cycles or the resources to manage that process. That's because each client has to have their own certificate that is personally issued and installed on their machine if you want to perform TLS authentication. All right, so that's one of the downsides to this process. And then, of course, all your AAA servers, ICE or Radius servers or whatever, have to have their own certificates as well. All right. If you're implementing this in Cisco environment, it's possible to actually tie Microsoft credentials for the users in with the certificate in the Microsoft database. So that's going to give you the option of having single sign-on capabilities and so on. At the beginning of the authentication process, EAP-TLS uses 802.1x to provide for the exchange of information, right? That's that framework that we talked about yesterday that identifies how messages are exchanged, right? It doesn't define the underlying protocols, right? 802.1x is a framework for exchange of messages. But that's what's going to allow this end-to-end EAP process. And in the wireless LAN portion, we use open authentication up to the association phase. That's why when we talked about yesterday, 802.1x looks to be like it's open authentication, but actually there's a back-end authentication component. So what happens is the client, and you can kind of follow along on the diagram here, the client sends a start frame to the access point to show that it's using 802.1x and the extensible authentication protocol. The authenticator, in this case the wireless LAN controller, right, returns a request identity message to the client. So the client sends its identity, user information, machine name, etc. to the controller, and then the authentication server verifies that information. Actually, before that happens, the identity is passed along to the authentication server, but before we start to go through some exchange, additional exchange, the authentication server sends its certificate to the client. That's going to provide identity and prove to the client that I'm communicating with the appropriate device. And then, of course, I'm going to send my certificate. The client's going to send his certificate back to the authentication server. There is remember, during this whole process, the client, which is the supplicant in this case, can't send real data. It can't send regular frames across the network. The door is still closed at the access point level. So even though I might be associated to the SSID, I'm not able to send actual data. All right? So at this stage, both the client and authentication server have proven their identities to each other. So they have a way now of sending encrypted messages to each other. All right? What kind of encrypted messages are we going to send? Well, they can send actual data. They can send some additional authentication processes. They can exchange a key pair, whatever it might be. We could use these public certificates to do bulk encryption. Server has the client's public certificate, the client has the server's public certificate, so we could follow that whole encrypt with a public certificate of the receiver, and they decrypt with a private certificate once they get the data. The problem is it's way too CPU intensive for fast data encryption and decryption. All right, public and private Public and private key pairs allow for the creation of an encrypted tunnel between the endpoints, but it's not nearly as efficient or nearly efficient enough to be able to actually send bulk encryption. All right, remember the AP in this case is transparent. It cannot read the encrypted dialog for the authentication process. In fact, in a wireless environment, the encryption must occur in the wireless space, which means it must stop at the AP level. And then the AP is responsible for encrypting and decrypting all the data packets. The AP does not need to extend further into the wired network. So using only certificates is not enough for the wireless encryption in an EAP-TLS authentication scheme. All right? We'll talk about how that's actually facilitated in a little bit. In fact, let me mention it now, right? The process is to use the encrypted tunnel between the authentication server and the client to generate that symmetric key that we talked about. That symmetric key is what we're going to use for AES and what we're going to use for our bulk encryption. From the exchanged certificates, and we go through some modulus, math and generate some random numbers and so on. Those are exchanged immediately after this authentication phase, and then both ends generate a common value. You can see that towards the bottom of the screen here. It's called a master key or a session key. It's called a pairwise master key because both the supplicant and the authentication server, the pair, actually the access point and the authentication server, which is the pair, are aware of what this master key is. Okay? The authentication server sends that master key to the AP if it's an autonomous access point, or to the controller if it's a lightweight access point. And then that's used to secure the connection. The encryption then occurs between the client and the AP, all right, or the client and the controller, right? The data gets passed back to the controller. So EAP-TLS is used in environments where we're trying to deploy and maintain certificates for all users and so on. There are other versions of extensible authentication that don't require the use of certificates, all right? In fact, we'll talk about the protected extensible authentication protocol and why that might be different. PEAP, Protected Extensible Authentication Protocol, is a compromise between, say, EAP-TLS and its complexities. PEAP relies entirely on EAP-TLS relies entirely on a certificate-based infrastructure. All right, and PEAP, conversely, does not require any certificate exchange between the client and the authentication server. What happens with PEAP is there is a certificate that's required, but only on the server side, right? The server's not presenting a certificate to the client is presenting a certificate to the server. The philosophy behind PEAP is to pretend to perform that TLS exchange, to create a tunnel where real authentication occurs. That secured tunnel effectively gets created in the first phase, but the client doesn't need to have or send a certificate. To an outside individual that might be looking in on the process, it looks as though the exchange occurs as if certificates were being exchanged. This was a protocol that was developed by Cisco and Microsoft and RSA, and it was supposed to make the whole implementation a little bit simpler, to make it less complex for administrators, especially if you have lots and lots and lots of wireless clients. All right, now there are actually two implementations of PEAP. There's PEAP GTC and PEAP MS CHAP v2. PEAP GTC authentication allows generic authentication to different databases, LDAP, one-time passwords, tokens, etc. Obviously, PEAP MS CHAP authentication allows authentication to databases that Microsoft incorporates, like Microsoft Active Directory and so on. With regard to 802.1x and the extensible authentication protocol types, dynamic encryption can still be used with PEAP. It's just a little bit more of a lightweight process. So let's take a look at what that process looks like we did for EAP-TLS. With PEAP, we have a pair of keys that have to be installed on the authentication server before any wireless exchange takes place. So there is still some level of authentication. Obviously, we just can't assume that individuals are who they say they are, right? On the client side, the client just simply has to understand and support that PEAP protocol. At the beginning of the authentication process, PEAP uses the 802.1x framework. So to allow end-to-end extensible authentication, the wireless LAN portion uses open authentication like we saw in the previous example for that association phase. The client sends a start frame to the AP to show that it's using, again, the 802.1x and extensible authentication, just like we saw in EAP-TLS. The AP returns a request for the client's identity. So far, everything looks essentially identical, right? The initial handshake between the client and the AP really looks exactly the same as EAP-TLS. That's why if somebody is kind of monitoring these transactions and they're looking at these transactions, it's going to look essentially the same. All right? All right. Specific to PEAP is that the client answer may be wrong, right? For example, if the client identifier is client1 at cisco.com or some other value comes in, like nobody at cisco.com or something else, it doesn't really matter, right? So we can actually hide the client's identity in this process. After receiving the client identifier, because we're not really using that to authenticate the client, although we do try to match that information in the server, after we receive the client identifier, the authentication server can recognize that ID or it may not recognize that ID, right? That's one of the differences here. It's going to send its certificate regardless. The client authentication, the client's authenticating the server using the certificate authority to verify the digital certificate of the server itself. In a TLS exchange, the client sends its own certificate, right? But in PEAP, the client generates a master encryption key. It encrypts that key using the server's public key, and then it sends the encrypted key to the authentication server. So this is a much more basic process in which we're kind of generating this pairwise master key. I mean, we are generating this pairwise master key, but the supplicant is not sending a certificate to the server, right? I think the diagram they have here is incorrect. I'm looking at it, and it looks as though they've made a mistake here. Let me see. Yeah. Well, it is accurate in the sense that the server sends the certificate, but there's no exchange of certificates from the client side. But we'll go ahead and continue on. All right. the process that I just described, right, where we go through the start process, request identity, identity gets sent, and in reality, the identity doesn't really matter, right? Whether the server recognizes the client ID or not, it's still going to send over its certificate. The client authenticates to the server using the CA, or the client authenticates the server using a CA to verify the digital signature of the server, and so on. All of this stuff that I just described is part of what we call phase one of the authentication process. The authentication server and the client now have a tunnel where they can exchange this encrypted information. Now, from an attacker's perspective, the transaction is complete. The client starts exchanging the data with the network. In reality, what's happening is that inside that encrypted tunnel, a second protected authentication phase starts. Okay? Phase two begins, and this is what you see in kind of the second box there. Phase two begins with an EAP server sending an optional EAP request, an identity frame to the client, which is protected by the TLS tunnel that was negotiated in phase one. So this data is already encrypted. The client responds with an EAP response identity message containing the user ID of the client. All right. We don't see the details of these steps in that second box, but this is what's occurring in that second box. The client server now actually knows the real identity of the client. Remember I said we don't care whether the identity of the client is accurate in that first phase, and that's because of this, right? Because we're actually verifying the real identity of the client in the second phase. Now, the client needs to prove that it is the user it claims to be, so it does this by sending credentials using GTC or MS Chat version 2. Not a certificate, but some sort of credentials. At this point, just like all the other EAP methods, both the server and the client have proven their identities, and they have a way of exchanging encrypted messages. Okay? Authentication server and client, well, let me think. Yeah, so the authentication server and the client at this point, they've exchanged all their values. They have random numbers that are sent back and forth to each other to generate this common value called the session key or the pairwise master key. And then that key is directly used to generate a web key or as an initial value for further negotiation between the clients and so on. All right. PEAP is widely used in wireless environments. It's not as secure as EAP-TLS, but it does offer a level of security that's high enough for most enterprise-type networks. Now you have a general understanding of the difference. I mean, obviously there's a lot of detail that we went into, but you have a general understanding of the difference between the two protocols. All right, so let's talk about EAP-FAST. All right. EAP-FAST, excuse me, which is the flexible authentication via secure tunnel protocol, or flexible authentication via secure tunneling protocol, was developed in, gosh, I can't remember the RFC, 48 something, but it was proposed by Cisco as a replacement for the lightweight extensible authentication protocol. I warned you guys yesterday, right, when we got into this 802.1x that there were going to be many, many different flavors that we were going to talk about. It can be very, very confusing, but you kind of have to go through it a few times to really understand it. So EAP-FAST, something developed by Cisco. It was actually designed to address some of the weaknesses of the lightweight extensible authentication protocol, but the purpose was to kind of maintain that lightweight functionality. Use of server certificates is optional with EAP-FAST. It also uses what we call a protected access credential to establish the TLS tunnel where client credentials get verified. So we're doing a two-phased approach here, just like we saw with PEAP, where we're establishing a TLS tunnel and then we're verifying the identity of individuals based on that establishment. Okay. EAP-FAST provides essentially the same level of security as EAP-TLS. But again, there's no need to manage certificates on the client side or, in this particular case, on the server side either. To make this happen, the same AAA server where authentication occurs is the server that generates the client credentials. And those client credentials are called PACs. That stands for Protected Access Credential. There are actually 3 phases of operation in EAP-FAST: Phase 0, Phase 1, and Phase 2. Phase 0, the PAC needs to be installed in the client. Now that can be done manually, or it can be done via some trusted connection where the client authenticates using a different method, maybe TLS or something like that, or MS Chat version 2. And that's typically what happens in most environments. Phase 1, the AAA server and the end user or the client use this PAC to authenticate each other and establish the secure tunnel. Very similar to TLS, to verify the identity of the AAA server, to establish a secure tunnel between the client and that server, and so on. The PAC actually replaces the digital certificate that was used in EAP-TLS, eliminates the need for the use of public key infrastructure or the need to manage these certificates. Then we move on to Phase 2, which is the third phase. The Radius server authenticates the user's credentials with another extensible authentication protocol process, which is protected by the TLS tunnel that was created in Phase 1. And this is a very common method of authentication. In fact, the most common method of authentication is either a password or some sort of token. A lot of people use tokens. All right. So a key element in this whole EAP-FAST process is the PAC itself, which replaces the certificates that we saw with EAP-TLS. PACs are unique shared credentials that are used to mutually authenticate the client and the server. Mutually authenticate. So we have the client authenticating the server and the server authenticating the client. A PAC gets associated with a specific client username, a server authority ID, so there is some tie-in to a specific variables that are defined by that particular user, but it removes the need for the digital certificates that are required using the public key infrastructure. So to create the PAC, the server authority identity, which we call the A-ID, we see that at the bottom of the screen there. That's the server authority identity, maintains a local key, which is called the master key. That's basically like a private key, only the server knows that key. When the client identity, which is referred to as the initiator identifier, or I-ID, you see that listed there as well, requests the PAC from the server generates a randomly unique PAC key and a PAC opaque field for that particular client. This is kind of like another key. All right. The PAC opaque field, in fact, contains that randomly generated PAC key, but it also contains other information like the IID, the key lifetime, and so on. Kind of like when you get a digital certificate or a certificate signed by a certificate authority, there's end user specific information within that certificate. There's a lifetime of that certificate, and so on. All right. Now that PAC opaque field gets encrypted with the master key so that it can be transmitted, and so on. Lots of information. I don't know if you guys are following or tracking what I'm saying here, but we could spend quite a bit of time talking about this process. Honestly, I don't know that it's really that important for you guys to understand as administrators all of the specifics and all the details here, because in reality, if you choose to implement EAP-FAST, right, can you change this process? Can you change how the process works? And the reality is no. But maybe if you have to troubleshoot, you might run into a scenario, I doubt it, where you would have to understand these basic concepts. All right. So let me just break down what a pack consists of. This is something that could potentially be on the exam, so we want to make sure that we cover it. Obviously, it's going to contain a key, right? That's the blue box that you see over here, this pack key, right? That's a 32 octet key, 32 octets, not 32 bits. So 32 octet to establish that phase 1 tunnel. So this blue key here is used to establish the phase 1 tunnel in the EAP-FAST process. Basically, if you're comparing this to TLS, this would be like the pre-master secret that's established. The AAA server randomly generates this pack key. Then you have the pack opaque field. That's the red box here. It's a variable length field that's sent to the AAA server during the establishment of phase 1 over the EAP-FAST tunnel, so that the EAP-FAST tunnel has already been established. This field can be interpreted only by the AAA server to recover all of the required information for the server to validate the client's identity and client authentication. So now we're going into the second, the second phase, I guess, where we're authenticating the client with the pack opaque field. Then the last bit of information you see down here, which is the pack info, this is also a variable length field. You see these dots here, that indicates that these are variable length fields. That's used to provide, at a minimum, the authority identity, which is the server's identity, or the pack issuer. There's some other information that can be contained here, like the lifetime can be conveyed by the AAA server to the client during the pack provisioning process, and so on. Once the pack has been created, it gets sent to the client. That pack can be sent during an auto provisioning process in phase 0, or we can go through a secondary process called a pack refresh in phase 2. We can also manually create those packs and install them on the clients manually. I think you'll find, if you're using EAP-FAST, that you will actually probably be going through the auto provisioning process and not manually installing these packs. Okay, so let's talk about that process. When an EAP-FAST session gets initiated, the server sends its ID in the EAP-FAST start packet to the client. The client uses that ID, the A-ID, to choose the pack to use for that particular session, assuming the pack has already been installed on the client, by the way. The client sends the pack opaque field from the appropriate pack to the server. Remember, that includes the pack key, the client identification, lifetime, etc. The server uses the master key to decrypt that pack opaque field and to retrieve the pack key. And then remember, that pack key is then what's used to set up the phase 2 part of the encryption, which is the encryption session. Now the server and the client have a shared pack key that was sent over the channel encrypted. And that's basically our shared secret key to establish our TLS tunnel. All right. So just like we did when we looked at EAP-TLS and PEAP, we'll take a look at the authentication process for EAP-FAST using pack provisioning and so on. EAP-FAST pack provisioning, very similar to a pair of keys that are installed on the client machine in EAP-TLS. At the beginning of the authentication process, EAP-FAST uses, again, the 802.1x framework. That's going to allow this end-to-end extensible authentication protocol. So the wireless LAN portion uses open authentication until the association process. The AP is still going to restrict all the traffic that's flowing from the client until the client goes to the authentication process on the Radius server. The client sends a start frame to the AP to show that it's using 802.1x and the extensible authentication protocol, just like before. The AP returns a request identity to the client, just like before. The client sends now, in this case, an identity address. In this case, it's in an email format to the AP and that gets passed over to the Radius server. All right. Now, in this particular case, it does have to match the identity of the supplicant. But at this point, the server and the client now have mutually authenticated each other using what we call phase 1 and 2 of that EAP-FAST process. All right. This authentication gives us the same results as what we saw with EAP-TLS. I mean, it looks exactly the same. In fact, in all of these processes that we've seen here, start, request, identity, identity, start, request, identity, identity. So we're seeing the same process happening in the beginning of each one of these different variations of extensible authentication. Okay. This is at the point, of course, where it becomes different, right? The next steps are the same for EAP-TLS and all their EAP types in the wireless network, right? The authentication server and the client use their exchanged values and random numbers that are sent to each other to generate a common value called the pairwise master key. That can be used to directly generate our WPA2 key, or it can be used as an initial value for further negotiation between the client and the AP. The Radius server is going to send over a session key to the AP in a success packet. The client and the AP use those keys during that particular session. EAP-FAST is actually considered to be a really robust authentication mechanism. The only constraint that we have with it, though, is the necessity to have a server that can generate and manage those packs. And of course, you got to have a client that's going to support EAP-FAST. Most Cisco clients, if they're using any Connect, for example, will support EAP-FAST standard. Cisco ICE does as well, and the Radius that's built into ICE supports it as well. So not a problem there. All right. So that concludes that lesson. I know there was a lot of information in this this particular lesson. Obviously, we talked about the public key infrastructure and how that's utilized in the environment. We talked about EAP-TLS, PEAP, and EAP-FAST. So why don't we just summarize real quick kind of the differences between these, right? EAP-TLS, we know, requires the use of digital certificates on both sides. PEAP doesn't require the client to have a certificate, but it does require the server to have a certificate. And there is some exchange in that process. EAP-FAST doesn't require the use of any certificates at all because we use those packs to provide the same level of security without those digital certificates. All right? So that concludes that lesson. Next, we're going to get into WPA and WPA2 and talk about what those protocols utilize and how they're used in our environment.